Okay, so you have the whole semester schedule there in front of you. I'm going to continue to give you these announcement slides, and so I hope that it won't be the situation where it's hard to keep things straight. The other thing that I want to draw your attention to, besides the fact that homework 8 has been postponed until Monday, is that the project, phase 2, has also been postponed. And so you've got a little more time there for phase 2 of the project. That will be due at the beginning of our class on Monday the 30th. So that's before our first electronic class on Monday, March 30th. Any other questions related to the announcements before we get into the discharge depth information?
Oh, I got one.
Okay.
When will you have the phase 1 graded?
I don't know.
Okay.
Yep.
By the end of spring break.
Will we get them, will we get them back before that for phase 2?
So the question is, will you have your updated, like, will you have my comments so you can update your flow demands before you finalize it? Yeah. Normally I would have had them graded by now, but redesigning the semester for 3 classes has slowed me down a little bit. So I think next week's going to be quite a lot quieter. So I think I'll probably be able to give it to you next week, hopefully the beginning of next week, and then that would give you about 10 days to update your flow rates. But if you don't have your updated flow rates in time for the network sizing, you can always remember in your final submission further optimize your pipe network. And so if you lay out where the pipes are and get an initial sizing done on your beginning estimate of the flow rates, you can update that later. Yeah.
So if we don't get our, like, where we need to fix our stuff, will we be penalized if we use the network that we already have?
No. No. I would hope that you would make any revisions by the final submission. But if you want to go ahead now and start designing your network based on the flow rates you gave me, you can. Any other questions? All right. This is a specific energy diagram, and we've seen this a couple of times on Monday's class and Wednesday's class. And specific energy, E, is we're measuring how much energy there is in the flow above the bottom of the channel. And so E is the flow depth, Y, plus the velocity head, V squared divided by 2G. Sometimes instead of V squared divided by 2G, remember we make the substitution Q squared divided by 2GA squared. So all we're saying is that for a certain flow rate, this curve was generated just for a fixed flow rate, but we were varying the slope of the channel. Depending on how steep the slope of the channel is, that varies the depth of flow, and it varies the velocity. And so there's lots of different specific energies that can exist depending on how steep the channel is. So the idea there was that we had a certain flow rate that was fixed, a certain roughness that was fixed, and the channel geometry didn't change. But with varying slopes, there were varying depths. And so therefore, we could calculate what specific energy there was associated with each of those different depths. So that's just a refresher. Now, this is a different figure that comes from your book, and this is slightly different because now what we have is a fixed amount of energy, but we're saying what flow rate could exist for a certain amount of specific energy. So, for instance, you are keeping the amount of energy constant and you're varying the flow rate. So, for example, if you had a depth that is really shallow, then you're not going to be able to get much flow rate through that for a certain constant specific energy. If the depth is really shallow, then that means that most of the energy is in the velocity head. So what we're saying is that everywhere on this curve has the same amount of E. but maybe it has a shallow depth, and so if the y is small, then that means the rest of the energy is in the velocity head. But there's not as much flow rate with a shallow depth because you just don't have a very big cross section. And then at the other extreme, if you have a very deep flow, then you're not having much conveyance. The velocity is low. And so the point is, on this figure, there's a certain flow rate that is the maximum flow rate that can be accommodated for a given amount of energy. And what that is that's the critical depth. So I want to introduce the idea is that the critical depth is the most efficient flow that you can have through a channel. If you're trying to maximize the flow rate for a certain amount of energy, that efficiency point is the critical depth. And we'll observe that when we go down into the hydraulics lab for a demo later in the semester. So critical flow rate corresponds to the minimum specific energy for a certain discharge. So this, remember, the critical depth was the point that matches up with the least specific energy. And if we were characterizing the flow regime, you remember Froude number greater than 1 means supercritical, Froude number less than 1 means subcritical. So the flow regime, another way we could classify the flow regime is whether the depth is greater than or less than the critical depth, which is the depth that corresponds to that minimum specific energy. So minimum specific energy for a certain discharge is critical flow. That's what we saw on the figure on the previous slide. But on this figure, the critical flow corresponds to the maximum discharge for a certain amount of specific energy. So critical flow is a really efficient flow condition, although it's not stable. These are interchangeable because it's the same thing. It's just different sides of the same coin, as you'll see today. So water is flowing down the river. This is a side view of flow through a channel, and the water encounters a step, and it's a step down. The question in this classic problem is, what will be the new depth if you have the water flowing upstream and the depth upstream is greater than the critical depth? So you notice how Y1 is bigger than YC? What does that tell us about the flow regime? Are conditions supercritical or subcritical at location 1? If the depth is greater than the critical depth, that means you have a slow flow velocity, and so that's subcritical conditions. So at 1, it's subcritical, and the way to remember it is subcritical means basically slow moving flow. And if the depth is deeper than critical, so this dashed line in the figure is just indicating what is the critical depth. So our actual observed flow depth is greater than critical, so that means you have subcritical conditions at 1. Because of that, you're also going to see subcritical conditions at 2 after this step down. But the question is how much deeper is the water going to get? And why does it get deeper? Like, why would this step down make the water deeper versus why wouldn't it be the same depth? Or why would it get shallower? So what we're learning is, how does a step down like this affect the flow conditions? A new flow depth after the drop, and what's happening is when the water flows down off of that drop, it's gaining energy. And it's not gaining specific energy, but it's gaining total energy. Because remember, specific energy is measured relative to the channel bottom. So at 1, there's only a certain amount of specific energy, but the specific energy at 2 will be greater than it was at 1 because of the drop down. So the specific energy at 1 is unchanged, but we can use Froude number as another way to classify flow regime. Anytime the Froude number is greater than 1, that's supercritical. If it's less than 1, that's subcritical. And here's our specific energy diagram. And this is an important animation I'm about to show you. I don't want to admit how long it took me to get all these arrows lined up. So enjoy this animation. This is me as an animator. We start with the initial depth, and I'm going to show you how we know it got deeper. We're going to follow this specific energy diagram. So the initial depth was Y1. we follow y1 over to the point of interception with a specific energy diagram, and then we go down to E1. So that's how much specific energy there was before the step. But the step down means that at location 2 there's now more specific energy. So E2, specific energy at 2, is how much there was at 1 plus the difference due to the step down. So now we have more specific energy, so we go up through the specific energy curve, and there's 2 intersection points. There's this lower one and the upper one. And we choose the upper one because conditions were subcritical at location 1. That means that they'll be subcritical at location 2. So this would have been the supercritical root of the solution. We're going to be solving a cubic equation, and we'll get a negative root, a supercritical depth, and a subcritical depth. And so you're going to have a cubic equation, and you're going to be wondering, well, which of the 2 flow depths sets up after this transition? And you would choose, in this case, the deeper of the 2 flow depths because it's subcritical flow upstream. It will be subcritical flow downstream. So here, arrow 4 is just showing what are the 2 different depth options, and we pick the larger of the 2, and we go back over to the vertical axis, and we would find y2. So that would be the new depth. And so the depth doesn't change by delta z. Delta z is how much the energy is changing. So we want to know what's the depth change by reflecting the corresponding energy change off of this graph to find out how the depth varies. So it got deeper because there's more energy. Does that make sense to everybody? Are there any questions about, let me do that animation one more time. We start with our known depth, reflect it down off the specific energy diagram and find out how much is at E1. Then E2 is bigger because the step down is like you're getting more energy, just like you would on a roller coaster. If you go down a hill, suddenly your car has more energy. So you've got E2 is bigger, then we go up, crossing the specific energy at these alternate depths. There's 2 alternate depths. We pick the deeper of the 2 because if conditions are subcritical upstream, they'll be subcritical downstream. And we can diagnose that the flow condition is subcritical by comparing the depth to the critical depth or by calculating the Froude number. Either one of those will allow us to understand what's the flow regime at 1. So that tells us to pick the deeper of the 2 routes, which we then take over to the vertical axis and get the y2 depth. I'm not going to go through it a third time, though. All right. So let's solve this problem by looking at if we have 30 cubic feet per second going through a rectangular channel. At location 1, we know that the depth was 3.5 feet. And this channel is 8 feet wide. What will be the depth downstream at location 2 if the drop is 1.2 feet? So it was flowing at 3.5 feet. It drops down. We want to find y2. So what you're going to do to solve this problem is, first of all, we have to verify at location 1 what was the flow regime. Is the flow subcritical or supercritical? So step 1 is calculate the Froude number. So calculate the Froude number. Step 2 is we're going to solve for the new depth by having the E1 is plus delta Z is E2. So what that'll mean is y1 plus v1 squared divided by 2g plus delta Z is equal to y2 plus v, well, we won't know v2 because we won't know the depth, and so I'll put it in terms of q squared divided by 2g a squared. And of course, a is 8 times y because of the width. All right, So step 1, calculate the Froude number, because we have to find out, is the condition supercritical or subcritical? Then step 2 is, here's our energy equation. Start substituting in all the knowns that we have into the energy equation, and we'll solve for y. And y is going to have 3 roots. All right, so first things first, we have to know what's the Froude number. So we substitute in the 30 cubic feet per second as the Q, square that. The T here means the top width. So that's the same thing as B, capital B, that you see in some formulas. It means the top of the channel. And since it's rectangular, no matter what the depth is, the top width is always going to remain 8 feet for this channel. So then G 32.2, and then the cross-sectional area is 3.5 feet by 8 feet, so that's 28 square feet, and we need to cube that term. So the Froude number of 0.101, since it's less than 1, that means the flow regime is subcritical conditions. Now we have to kind of remember that, because later on, when we do all the substitutions into the specific energy equation, we'll have 3 roots. So I'm not going to show you all the solution yet. I want you to try and set up and solve those 3 roots to find out what are the possible depths that would make the energy balance out the way it needs to. But the clue of which depth to choose comes from this Froude equation where the conditions are subcritical initially. Okay, so we know the initial depth at 1 is 3.5 feet, and then we substitute in the velocity head. So that's the velocity squared divided by 2g. So over on the left-hand side of the equation is 4.718 feet, and then on the right side of the equation is y2, and then, oh, by the way, it looks like I also moved the delta z into there. So the delta z that has been combined, since that's a known 1.2 foot depth. Yeah, 1.2. So the y's are on the right-hand side of the equation. There's one of them, y2 squared, in the denominator of this term. So we have to multiply, to get that out of the denominator, multiply each of these terms by y2 squared. And so that makes this y2 cubed. And then this one is y2 squared. And then to get it on the right side of the equation, it goes from a positive to a negative. And then there's 0.2184, which now is just the number. If I had multiplied each term by y2 squared, the one in the denominator drops out. So this is a cubic equation. And we need to find all of the roots to know which one to select. So for this cubic equation, the possible roots are negative 0.211, and that doesn't make any physical sense in the case of flow. But then there are 2 non-negative roots, one which would correspond to if the flow conditions were supercritical, and one that corresponds to if the flow conditions were subcritical. And so the way that we know which of these is the right answer is by going back to the original calculations we did with the Froude number. And so the Froude number upstream was subcritical, which, remember, subcritical flow is when it's deep and moving slowly. So which of these 2 depths is going to correspond to deep, slow-moving flow? It's the bigger one. And so the flow depth is going to be 4.708. So the flow depth after the drop, 4.708 feet. So that's a process probably that I'll include in maybe one of the extra credit bonus problems that I have you solve next week. Just practicing these cubic equations and finding what's the new depth after it goes through a drop. By the way, on those extra credit assignments, even if you don't get it perfectly right, I'll still give you some points. So it's partial credit on those. All right. Does anybody have a question on this example? A similar concept applies if it's a step up. So this was a step down. The same principles apply if it's a step up. We have a certain amount of energy at 1, and how much energy is available at 2 is the amount of specific energy there it was at 1 minus the delta Z instead of plus. So the water has to flow up over that obstruction. It's losing specific energy instead of gaining specific energy. So the total energy doesn't change, but the specific energy does. And so if we look at the specific energy diagram, remember the animation that I was so proud of earlier? So I don't have this one animated, but let's follow what's happening. There was the Y1, and we go down to find the equivalent specific energy. And this time we shift to the left because of the drop, because of the step up, you're losing specific energy. So the delta Z shifts it to the left, and then we have it going up through both of these two options. There's the subcritical and the supercritical route. And since we had subcritical flow at 1, then we go to the left and find the new subcritical route. And so the depth is actually shallower. And this is really counterintuitive. Think about it. The water has to flow over an obstacle, but because it flows over the obstacle, now it's a shallower depth, which means it has to flow faster. So having the step that the water has to flow up over the step actually increases the velocity of the flow. So that's one of the first of a few kind of head scratchers where the water is doing something that initially you maybe wouldn't have come to that conclusion when you first looked at it. 150, we're out of time. Today's the 13th of March. I'll see you again on the 13th of April, if not before, virtually, electronically somehow. Good luck to everybody.